the webinar. For today, our speaker, Nicolas Flament, currently he's a senior lecturer at the stuck. I think I'm okay.
Something happened, but I lost you there for some time. So I missed the introduction.
Okay. I will reintroduce our speaker today. Sorry, probably my internet has some unstable problems. But okay, Nicolas, I think you go ahead. Let's keep everything in time.
Terrific. Thank you so much for the invitation again. I will just hide these panels away and get my pointer just to be ready. Here you go. Good morning, and thank you for joining this morning. I'm very excited to be talking today about setting the lower mantle free. This is the output from a research project that was funded part by industry, by De Beers, looking for diamonds. So it's a frontier diamond exploration project, and by the Australian Research Council, which is supported by Australian taxpayers. This work was carried out by 4 early to mid-career researchers. Omer Bodour is actually in the office next to me just now. Simon Williams, who is a future fellow at the University of Tasmania now, and Andrew Meredith, who is a Marie Curie fellow at Leeds University. I'm going to be talking a fair bit about blobs today. And let me start by saying what I mean by blobs. It's been known for about 35 to 40 years that deep beneath Africa and deep beneath the Pacific Ocean, there are 2 areas that are seismically slower than surrounding mantle. Technically, they're called large low shear velocity provinces. From a seismic point of view, I'm going to call them blobs because in my mantle flow models, I would have to call them something else. We can see the blobs here. The one under Africa, the one under the Pacific, they have some extension up into the mantle, and obviously that depends on which velocity contour is chosen to define the blob. And here is an image from S40 RTS that put together by Rodri Davis and collaborators. We can look at the blobs in many different ways, in many different models. Here's a look at them in 2D. Again, in the same model, S40 RTS. What I've done here, I've picked a depth about 200 kilometers above the core mantle boundary. And this map here shows the seismic velocity anomalies. And you can see again that beneath Africa and beneath the Pacific Oceans, there's 2 areas where the mantle is seismically slower than surrounding. And away from that, you have areas where the mantle is seismically faster, and that fits well with subducting slabs. A few years back, there was an important insight into these blobs. My apologies, I've got a window here that's in my way. I would like to get it out of the way. So I'm just going to do that. Hide video panel. Sorry about this. Hide floating meeting controls, and I'm back with you. There was an important insight. That's work that was first published by Burke and others, the late Kevin Burke and others in 2008. So the idea must have been out from about 2006, that there seemed to be a link between large igneous provinces. So these are outpouring of lava of the type, this one here, I believe might be the Deccan Trap. And that's been linked to the extinction of the dinosaurs. So these are considerable outpourings of lava at Earth's surface. When these large igneous provinces are reconstructed to their time of eruption and showed at present day, which is what we're looking at here, they tend to be around the blobs. There's not many of them. There's about 25 of them in the last 300 million years, which is why the authors here also consider kimberlites. Kimberlites are much smaller volcanic features, but there's many more of them. There's no kimberlite in the Pacific hemisphere because kimberlites are mostly associated with thick continental lithosphere. What you can see is that the kimberlites also tend to cluster around the African blob, with the exception of a few up here. And so here the contour that was picked was S mean, and it was -1% to define the blob. And so this was very interesting and exciting. It suggested that there was a link between the deepest Earth and volcanic activity at Earth's surface. Now, it became an exciting potential reference frame for longitude. Let me explain. Before 200 million years ago, there's no seafloor that's preserved, which means that devising tectonic reconstructions becomes very difficult. One is left essentially with paleomagnetic data from blocks. These paleomagnetic data, they are good to constrain the latitude, but not the longitude of blocks. Now, the previous slide shows that there really seems to be a correlation between blobs and volcanic eruptions at Earth's surface. And if one accepts that, it might be possible to link any volcanic product to the edge of a blob if one also assumes that the blob is rigid and fixed over time. And so that was the hypothesis put forward by Torsvik and others, that perhaps if one considers the blobs not to have moved, if one knows the latitude of a block that carries a large igneous province or a kimberlite, then its longitude could be deduced by putting the blob on the edge of the nearest blob, because the correlation was proposed to be more favorable with the edge. This is a bit of a problem with the current understanding of geodynamics. This is a paper by McNamara associated with the paper I'm presenting here. And Alan explained that the current understanding is that the blobs are shaped by subducting tectonic plates, subducting slabs sinking into the Earth mantle. And essentially, as they sink, they push the mantle in front of them, and also eventually they may come close to a core mantle boundary and actually push the blobs themselves. Now, if one accepts that this is one way of moving blobs or forming blobs, it will all depend whether blobs are static or not, where subduction zones were back in time. Now, obviously, what I'm presenting here is a model. It's a tectonic reconstruction or a tectonic model. And what I'm showing is the location of subduction zones reconstructed in time with the warm colors for present day and going colder and colder back in time. The top panel is the last 200 million years, I believe. What you can see up here is that the subduction zones fall away from the blobs. The blobs here are shown, it's a map from Lekich and others in 2012, from 5 tomographic models where all 5 agree that there's a blob. It's this outer contour here, and where only one agree, it's this inner contour here. At the bottom, we're looking at the previous 200 million years of a particular tectonic reconstruction. And what we can see there is that there's a lot more motion of subduction zones, and also subduction zones fall over the blobs. And so if one accepts the previously proposed mechanism, it seems difficult to avoid that at some point in the history of the Earth, or if for this tectonic reconstruction, the blob would be down there, for example, because there would be a subduction zone if it sinks vertically. So we tested that hypothesis, that idea that blobs are fixed and rigid through time. How did we do this? We used convection models that have been modified to read in tectonic reconstructions at the surface. So these models are driven from the top, and it's important to keep that in mind as we look at the results. At the top, we use the velocities, and we have the velocities because the plates close continuously. And then we also make ages of the maps, of the age of the seafloor back in time. We use this to impose subduction zones into the model as well as velocities. And so the thickness of a subduction zone depends on the age of the ocean floor through the house-based cooling model. What this is trying to show at the bottom is what went in and what comes out. Okay, so the input is on the left-hand side, it's tectonic reconstructions, and the output would look something like that. We're looking into the mantle now, and what we're looking at is an isosurface of temperature. That's for the cold slabs sinking into the mantle, and they are colored by depth, with the shallower being lighter and the darker being deeper. These models I run on a supercomputer in Australia. We're lagging a bit behind what you might have access to in China, so go get the better models when you can, or if you can. These ones were for 13 million points, and they cost about 75,000 CPU hours for each model for 1 billion years of history. There's a few things to these models, but I'll highlight what is really needed for the purpose of this talk. I'm happy to talk further about them. One important thing is the initial condition that is built from the tectonic reconstruction. So you can see an annulus section through the temperature field here of the temperature field at the equator in the initial condition, and we've inserted slabs with an angle of 45 degrees till about 450 kilometers depth, and then we put them straight down, and then we make them a bit thicker in the lower mantle where we've made the viscosity 10 times greater. There's an adiabat, so temperature increases with depth. And one more thing I need to tell you is that in the lowermost mantle, in some cases, there is a chemically distinct material that's denser than the surrounding mantle, and I vary that density, and in some cases it's purely thermal. Here's that same initial condition seen in 3D, and you see the slabs inserted into the Earth's mantle and thickening into the lower mantle. And you also see the continents here, and it's important that at this point I let you know that the continents also have some chemically distinct material, and they are lighter than the mantle. About 7% lighter actually, which is significant. Another important aspect is the subduction history we impose into these models. I used the first tectonic reconstruction extending back to 1 billion years, and that was the tectonic reconstruction of Andrew Meredith and others. And we modified it, and I will come back to this in the talk, to remove what is known as the net rotation of the lithosphere. The net rotation of the lithosphere is the degree 1 motion, if you want to think in terms of physics, or the wholesale motion of the entire lithosphere with respect to the mantle. It's known to be non-zero, but it also is known to arise in the mantle. So if we remove it at the surface, it might arise naturally from the mantle convection model. Now, here's the subduction history as the earlier slide, but now we go back to 1 billion years and we don't have as many lines plotted. And what you can see is that at times early in Earth history, or early in with this reconstruction, subduction zones overlap over the blobs as imaged by the vote maps of Lekic and others. Okay. And I'm going to go straight into some results just to keep you engaged and interested, and then I will unpack these results for you. Omar produced a beautiful video of what the mantle convection model looks like for the last 200 million years in 1 million year increment. There is a lot going on here, so I'm going to show this video a couple of times, and then I'll show stills or snapshots from this. At the surface, we have the coastlines reconstructed through time, and they are split into tectonic blocks. Okay, here you can see Africa that I'm outlining now. Between the plates, we have plate boundaries that are shown in green, and they evolve through time, and the plates close continuously. Now we can look into the Earth. Into the Earth, we have slabs, as I showed earlier, which are cold features. They are colored by depth, and darker is deeper. And then we have the blobs and plumes. Plumes arise from the blobs, and the blob, or I've also called them sometimes basal mantle structures for these models. Colored by depth, they are hotter than ambient mantle, and the darker colors represent shallower material. And I just want, on the last iteration of this movie, to highlight a couple of features, and I'll let it run once more, perhaps, is that when we start at 200 million years ago, we're looking at the African hemisphere, and at 200 million years ago, there wasn't one blob, but there were about 3 different smaller blobs. And these smaller blobs were separated by remnant slabs that had sunk into the African hemisphere earlier into the history. And these slabs warm up. In some cases, they actually get assimilated with the blob. And you can also see the push of the blobs, and they amalgamate together. And at present day, we get something that's one blob. So that was really quite interesting. So just to reiterate, at 180 million years ago, the African blob is not really one feature. There's really some slabs here, especially on this eastern part, that splits the blob in two. And still at around about 120 million years ago. And still at 60 million years ago, although you could start debating whether this would be resolved with tomography, and you can also debate whether the African blob, so to call it, is really just one blob or a cluster of smaller blobs at present day. As more resolution comes into the tomography, this is being questioned. And here's the picture from that model at present day. Another way to look at the results of the same model is to make a 2D slice. And again, I'm making a 2D slice 300 kilometers above the core mantle boundary. And we can see the African blob and the Pacific blob. Earlier, I showed you a similar image from a tomographic model. Now, there's 2 ways to compare the 2 entities. They are in 2 different physical quantities. Here we're looking at seismic velocity anomalies. In the previous slide, we were looking at temperature anomalies. The proper way to compare the 2, or one way to compare the 2, is to convert the model to so from the density, from the velocity anomalies in the model, I get back to seismic velocity anomalies, and then seismically filter that with a filter such as a filter for S40 or S12 RTS. This is work in progress for me. And so at that stage, I used a different strategy inspired by Lekic and others, which is cluster analysis, or k-means cluster analysis. So what I did here is consider a large number of points at the surface of the Earth. I think they were 50 kilometers apart. And consider the variations with depth of one property. So in the case of tomographic model, the property is seismic velocity. And the depth range considered was between 1,000 and 2,800 kilometers. And then a k-means algorithm was asked to distinguish 2 clusters. And the way this works, it minimizes the distance to the mean for each cluster. And in doing this, 2 clusters emerge that are mapped here. And one is low seismic velocities, and the other one is high seismic velocity anomalies. The point to note is, in doing this, the blob here for S40 RTS the blobs cover 34% of Earth's surface, and that's similar to what the continents cover at Earth's surface, which is 27% emerge and 42% also if one also goes to the COB. Here's the results from the flow model. Cluster analysis now is for temperature, and there's a hot cluster and a cold cluster. And the hot cluster here is mapped in gray. Interestingly, for this flow model, this particular model, the fraction that the blobs cover is also 34%. Now, this fraction is important because what I'm going to do next is compare the 2 results. And to compare them, I need to make sure essentially that if the target is tomographic model, which it should be because it's from data, whereas the other one is from theory only, it's important that the mantle flow model covers an area that's similar to the target area. Now, the next game I've played, and there's different indices that one can derive. Here I'm presenting the accuracy, what I've called the accuracy. Essentially, it's trying to work out a match between the flow model and the tomographic model. Success here is either orange or gray. Orange is blob, gray is non-blob in both the mantle flow model and the tomographic model. If one takes these two, the area of the orange plus the area of the gray over the total area, in this case, one gets 72%. However, it will not escape you that the area of gray is much larger than the area of orange. Okay, so part of the success of the model here is to put the slabs in the correct place. Another metric would also consider the false positive, which is here, and the true negative, and the false negative, which is here. The false positive is where the model predicts a blob, but the tomographic model does not. And a false negative is where the flow model doesn't predict a blob, but the tomographic model predicts a blob. So other indices exist. I've used the accuracy that's driven up by the gray. One could use the sensitivity that focuses on orange, green, and blue, I believe, and the results would drop to closer to 50%, but the trend between models would remain the same. Now, this was a constraint for the present day, and I would like now to try and have a constraint over time. And this is inspired by the work of Torsvik and others. What I'm showing here is the blobs for S40RTS in the back, and at the surface, I'm showing reconstructed volcanic eruptions. I have two sets of them. I have as diamonds, I'm showing the large igneous provinces from Johansson and others in 2018. They're colored by age, so colder colors are older. And there's 168 of them because there's the plume heads, so the lips per se, but there's also the plume tails in this one. So if you think Hawaii emperor seamounts, they are part of this data set. Okay. And then the second data set, which is many more points, is the kimberlites, again colored by age, and these are from the Tapper et al. Database. There's 763 of them in this case. Just taking a look at what this looks like over time. So we've got the number of volcanic eruptions over time. We go for the last 320 million years ago. The data here has been rebinned within 10 million years to match the model output, which is every 20 million years. Okay, so we have 20 million year increments here. So the large igneous provinces, there's up to 30 of them at any point. The kimberlites, there's up to about 160 of them. And then when I combine the two data sets, which I will do for the analysis, there's up to about 180, close to 100 million years ago, maybe 80 million years ago. Excellent. So now I've got a time-dependent constraint on the success of the model. So the idea to succeed, and that's the point that Torsvik and others made, is that the volcanic products should be close to the blobs. Okay. On this video here, I'm going to show you blobs on the right-hand side from the tomographic model, which is S40RTS in this case, and then the preferred mantle flow model on the left-hand side. So the blobs won't move on the right, and they will move on the left. When I go into actually presenting distances, and maybe I should introduce what I did. For each volcanic eruption, I measured the distance to the nearest blob. Okay, and the distance was to the edge of the blob. And the distance was positive if the volcanic product was inside the blob, and negative if it was outside the blob. So let's take a look at this. And as you look at this, perhaps start focusing on the left where things move, and try to see, are the volcanic eruptions close to the gray blobs? And now we're going back in time, and it will stop at 320 million years ago. And on the second one, perhaps you can try and compare. I can't look at both at the same time. You could also try and see, well, and what does the match look like on the right-hand side where the blob doesn't move? Okay, and I would say that visually, it seems like moving blobs are close to the volcanic eruptions, and non-moving blobs or fixed blobs are also close to the volcanic eruptions. So to summarize this, I created EDFs or CDFs, which are cumulative density functions for these volcanic eruptions. This is considering the entire time series and presented as one distribution. I'm showing this for the flow model. Now, to do that, I considered a set of random points, which there was 931 points, which is the same as the two databases combined. And I enforced that the distribution of the random points was the same as the combined databases. So in time, they have the same distribution. In space, the points can fall anywhere onto the Earth's surface. Let me play this now, going back in time. And you'll see when we get to about 100 million years ago, it's going to go chickenpox. And there's random points all over the place. The reason for that is that the kimberlites tend to occur in clusters. So there's many kimberlites next to each other. And this becomes very apparent when we take the number of kimberlites and distribute them all over the surface. There's many kimberlites that actually fall on South Africa, for example. Now, for each of these red points, I measured the distance to the nearest blob. What I'm showing here is one iteration, but I would do 1,000 iterations. And this 1,000 iteration is represented here. And then I carried out a test. And the test goes as follows. For each iteration, random iteration, I measured the mean of the absolute value of the distance to the blob. I took the absolute value because I had negative and positive values here. And then I compared it to the mean of the absolute values of the actual distribution, so the blue one. And I ensured that the mean of the absolute values of the blue distribution was less than that of the gray distribution. That was one part. And the second part was to carry out a Kolmogorov-Smirnov test. And that test essentially assesses the null hypothesis that the blue distribution and gray distribution are taken from the same sample at a confidence level. So I did that at 95% confidence. And essentially I could reject that hypothesis and establish that the blue curve was statistically distinct from the gray curve. That's a success. And if it's not, it's a non-success. Okay. And I reported a fraction. So that's out of 1,000, but I give it as a fraction. So in this case, you can see that the 1,000 iterations are further in a mean sense and statistically distinct in a Kolmogorov-Smirnov sense. And then for the tomographic model, it was 30 failed. So it's 970 succeeded. That's because there's some overlap in the middle. And in some, for some, maybe the mean test was failed as well. Okay, so I've introduced a lot here. I've actually introduced 4 metrics, and we're going to look at these 4 metrics now. For a series of tomographic models at the top, and then 2 series of mantle flow models. The 4 metrics are A, B, C, and D. And actually, I had a bit of a typo in the published version of the article, which is embarrassing, but you know, it's life. We are human. So that's the corrected version of the figure. And what was different was the x-axis labels for these 2 panels, I believe. Okay, so the 4 metrics are the area covered by the blobs, the accuracy, so how well the blobs match other blobs, the median distance, and then the success, the fractions of the success for the statistical test. So I carried that out for tomographic models, you can see at the top, and then the gray bands in each case come from the range in the tomographic models. So here I'm assessing the area in all tomographic models. You can see that gypsum S covers a greater area for some reason. Then I'm assessing the accuracy, and you can see that the accuracy is in a 80 plus percent, 80 plus for 0.8 and plus for all tomographic models against one another, except for gypsum S. And then the distances. So the blobs, the volcanic eruptions tend to be slightly out of the blobs, except for gypsum S, because the blobs are greater, so they're in the blobs with a positive. And then the stats. The stats are passed for all models except for SEM-UCB WM1, because the mean in that model tends to be greater in the sample than in the random. Now I carried out, here I'm presenting 9 mantle flow model. The one I've been showing you is C7. In 1, 2, and 3, I tested the viscosity of the basal layer. And I established that there was a sweet spot when the basal layer was 10 times more viscous than the ambient mantle. Okay, it was hardly any difference in area. It was better for accuracy and it was better for the distance. So I went with that. And then I varied the density of the basal layer. And there's a bit of a trade-off. C6 is a good match for accuracy, but the area is too small. So in the end, C7 was my preferred. In the area is within range of tomographic models, and the accuracy is just below the range. I didn't find a model that is in range for all of them. That would have been over tweaking. I think there's too many uncertainties to try to do that. Statistically, they all pass, which is great. And you can see again, if the area increases, the volcanic provinces go, the distances become positive in a median sense, which means that more than half of the volcanic eruptions are in the blobs. I'm going a bit slow, but I'll get there, I'm pretty sure. Bear with me. I want to show you one sensitivity test, which is the tectonic reconstruction. So using the original paleomagnetic reference frame from Meredith et al., this is what the map at present day looks like. And if one goes to no-net rotation, this is where the volcanic eruptions would reconstruct, shown at present day, reconstructed to their time of eruption. So you can see they pushed further out from the blobs. That's the effect of net rotation. So now when I did that test, at the top here, I have the paleomagnetic reference frame, and the first 2 panels don't change, or A and B, the first 2 columns. And then in the middle, I have no net rotation. And you can see that with net rotation, the volcanic products end up in the blobs for tomography, and outside mostly for if the net rotation is removed. And that's this effect that the volcanic products tend to be pushed outside. And then I carried out 2 mantle flow models, one in the original paleomagnetic reference frame and the other one with net rotation removed. And you can see the main thing is that the accuracy really drops here for the model with net rotation. And let me show you this graphically. This is the match I had shown you earlier for the original model. And then if we carry out a similar model with net rotation, what happens is that the blobs end up shifted. And then the drop is actually significant from 72 to 58. And you can see that the African blob and the Pacific blob really aren't where they would be expected. And that's a known problem. This is a publication from Rudolph and Zhong. It's a bit different in that they did not remove the net rotation from the tectonic reconstruction, but they removed it within the mantle. Okay, but the net effect, so to say, is the same. With net rotation, one gets a shift of the structures, and with that net rotation, the structures end up in a different place. So that's why I prefer the model without net rotation. There's 2 more things I'd like to talk about, 2 more implications of these models. One is that idea that there's a link between the continental's configuration at the surface and the deep Earth. So a potential link between supercontinents and blobs, again, going back to work by Zhong and others in 2007. So the idea there was, without continents, perhaps we have a degree 1 Earth with a super downwelling and a super plume. And if there's a girdle of subduction around a supercontinent, perhaps there is still a superplume, but a second plume under the supercontinent. And that's a degree 2 Earth. I'm not exactly going to investigate this, but I'm going to investigate the link between what's at the surface and what's deep in the Earth. Further work from Zhong and others, or Zhong and Rudolph, had, and this was very similar to what I'm presenting today. One key difference is that the reconstructions at the surface did not extend as far back in time. And the suggestion from these models was that by 200 million years ago, there seemed to be an African blob. Okay, and so the argument in Zhong and Rudolph was that, well, before 200 million years, there was some mobility, but perhaps in the last 200 million years, there was not much mobility. Now, the main difference, as I said, is that what we have is a reconstruction going further back in time. And here I'm showing 4 time slices. I'm going to focus on the 2 on the left-hand side. 740 million years ago, in this scenario, there are subduction zones around the West Gondwana blocks, and I'll come back to these. And then at 400 million years ago, there's 2 key subduction zones in the reconstruction: the Paleo-Tethys northern margin and the Gondwana western margin, which is here. So the ones around the West Gondwana blocks, what we did, and that's a gorgeous figure from Omar. What we see is the slabs in the deep mantle, again in the blobs, and then we've tracked slabs. The result is shown as the temperature at 500 million years ago, and these are the path of slabs from 740 million years ago. So over 250 million years or so, they've sunk into the Earth's mantle and are now down there. We call that the Western Gondwana slabs. And you can see when you track them, we can still see them at 80 million years ago, because that was a lot of material subducted down there. And so it diffuses over time, but very slowly. And now we have a push from the West Gondwana, I'm getting confused, from the Gondwana western margin slab here and the Paleo-Tethys northern margin slab here pushing. So let's try to look at this in a movie. That's going to jump a fair bit. So I'm going to show the movie a couple of times, but then I'll show you stills. Very similar as earlier, except that the plate boundaries are in blue, and it jumps a lot more because the temporal resolution is now 20 million years as opposed to 1 million years. Okay. And actually, this is moving too fast, so I'm going to go to stills. And what you saw, these West Gondwana slab, they originate from around these blocks. They sink into the mantle. A lot of material gets down. You can see that this is a significant blob. This is what's in that scenario. And it persists at 460 million years ago, 280 million years ago, and it will then divide into a northern part and a southern part. But in the south here, I think there's still a raft that comes from that. And that's why in our results, we don't get a coherent African blob before. And we tested a large number of models, and it comes together systematically in the last 100 million years or so. Bear with me, there's one more thing I would like to do, and it's to talk to you about some potential geochemical implications of this work. You may have heard of the Dupal anomaly or things like that. Essentially, work going back to the 80s identified that hotspots in the southern hemisphere look different to hotspots elsewhere. So there's that band of latitude here where looking at lavas and the lead 108 to 104 anomalies were positive in that band for the hotspots and negative away from it. And so the interpretation was that there's a southern part and a northern part to the mantle. This was revisited a couple of years ago by Luc Doucet and others at Curtin. Well, Luc is at Curtin, maybe some of the collaborators there aren't. What Luc and others did is select a number of plumes, and I use the word select because it's important. The results of this work depend on which plumes are selected. As being primary plumes, either in the African hemisphere or in the Pacific hemisphere, African in red, Pacific in blue. And what Luke and others showed, looking at again 08 to 04 lead anomalies against 06 to 04, and the previous week it was 07 to 04. And we have the northern hemisphere reference line here. And in the Pacific realm, it seems that generally the data plot along that northern hemisphere reference line. However, in the African realm or hemisphere, it seems to plot away from it, at least in this area here. And one way to explain this would be to add some contamination from upper continental crust. That was the proposal from Doucet and others. I told you earlier that in our models, the continents were chemically distinct, and so we could track where do the continents end up. They're lighter, but somehow they end up being entrained by subduction zones. And we can look at essentially how this light material might be pushed down by sinking slabs. So that's what we've done here. These are the areas with at least 5% of continental crust colored by depth. On the left-hand side, you can see in the African hemisphere, there's actually the African craton or the African oldest blocks in purple, and then the coastline is in white at the surface, and plate boundaries again in green. You can see there's a fair bit, quite to some quite large depth, colored by depth. Whereas in the Pacific realm, there's a lot less. It's expected because in the last billion years in this model, there's been a lot less continents above the Pacific hemisphere than above the African hemisphere. So let me just show you an animation of that with the African hemisphere on the left and the Pacific hemisphere on the right. And we're going to see that snow. That's from the West Gondwana block. You can see some of these anomalies sinking in, and it's like it's snowing continental crust into the deep mantle. Okay, well, there's continental crust entrained to large depths in the African hemisphere in particular, and a lot less in the Pacific hemisphere. So a few conclusions from this work. The main one is that the history of volcanism is as compatible with moving blobs as it is with fixed blobs. So the blobs may be moving, they must not be fixed. And this is consistent with the current understanding of global geodynamics. I must stress that the models I presented are driven from the top. It might be possible to devise models that are fully consistent dynamically and that drive tectonics from the bottom. This is a challenge for geodynamics. The blobs could come together and break apart similarly to continents at the surface. And the African blob may have come together in the last 100 million years, rather than having been fixed and assembled for perhaps 500 million years, 550 million years, or even more, as proposed by others before. And finally, the African deep mantle domain could be enriched by the subduction of continental material. I thank you very much for your attention, and I would be very pleased to entertain any questions you may have.
Hi, Nicolas. Can you hear me?
Yes, I can hear you.
Yes, great presentation. Thank you so much. And yes, I'm Chen, so I'm a postdoc right now at Caltech working with Mike Gurnis, and it's great to see your presentation for your paper. So I have a question for the content materials. So yeah, I also read that Luke's paper, so in Nature Geoscience, and also he invited me to give a presentation in this month. So because the LSB are in the lower mantle, yeah. So for the content materials, it's lighter. So I know some process can get the content material in the upper mantle, but if you want to get the content materials in the lower mantle, I kind of feel it's pretty challenging. So could you explain in your model, so how the content materials get into the lower mantle?
Yeah, that's a great question, and you've gone straight to a I've stuck my neck out by presenting that. I don't know if I would expect them to go to the lower mantle. Okay, they do in models. And I must disclose that in the assimilation workflow that Dan Bauer, Mike Gurnis, and myself, I contributed modestly to that work, put together. The continents at subduction zones tend to be entrained more than we would want them to. Okay, so there's a bit of an artifact there. I think the first order result is that it's possible to entrain material down to depth. As to then, I suppose it will depend. It will depend on what happens to that in terms of phase changes and all. So you've asked me a very pointy question there. All I will say is that if in some way the buoyancy of the negative buoyancy of the slab exceeds the positive buoyancy of the continental material, it could be possible. I've not looked at the details of that, so I will leave it as a very good question and to be looked at in more detail.
Okay. Yeah. Thank you, Nicolas. Yeah.
Can I
Yes,
ask
please.
a question?
Yeah, absolutely. Hi. Please.
Hi. Thank you. Great work. Thank you for your presentation. I have a question about after your talk, because since the mantle material are moving laterally,
yes,
and it takes a long time for material to move upwards. So is it possible that when the magma erupted on the Earth's surface and the location won't be too close to the blob's boundary? That is to say, like, is it possible that mantle upwelling is oblique or lateral transit or moving for a long distance?
that is a great question and a great observation. So I've been working on the slabs. So the slabs go about 10 times slower in these models, I think, to sink than the plumes take to come up. Plumes, I think, generally will come up within 20 million years. I think that's what I wanted to show. Sorry, I'm jumping a lot here. A few things to consider here is that the lateral viscosity variations in this model, they're limited to 3 orders. So the plumes may be 3 orders of magnitude less viscous than what's around them. In nature, it might be a lot more. So in nature, the plumes might rise a lot faster. Okay. So the model will tend to have too much lateral motion of the plumes because they're not rising as fast as perhaps they could in nature. That's one aspect. The second aspect is that net rotation, again, that I talked about, which is always something to consider here. So even if it's removed, I'm working on what the slabs do, and what I've noticed is that there is a lot of lateral motion in the slabs, which will be a problem. And then the last point I would like to make, and that's, I think essentially your question is extremely pertinent, because what it points to is, well, really the link shouldn't be between the blobs and the volcanic eruptions and the blobs. And I'm now working with a student at looking at the link between the plumes and the large igneous provinces, or the kimberlites as well. And I must say, I've done work with Mike and others before on the plumes, and I assume many of you might be doing work on that as well. It sounds like from your questions. And the plumes, they don't come up in these models. They come up generally in areas and at times that are compatible with large igneous provinces. But of course, it is stochastic, so it's not a process we control. We tried to control the process and we didn't succeed because the overall buoyancy of the overall flow of the model couldn't be overcome by one buoyancy anomaly. So sorry, this was the long answer to your question. The question is very pertinent, and there's more to explore in that space. Yes.
That's very thoroughly. Thank you. Following the plume question, so I don't know whether you have tried different plume list or different list for large igneous provinces. Will the result be different?
Okay, so that's how I started actually.
Okay.
I started having 4 different databases. I use Dubrovino and others, 2016, but there's only about 30 points in there. I used Ernst and Newby. There's a few less than in Johansson and others. And then I used Tapper and others. When I had these results to track, the story was very difficult to tell. It was too much to put in a short paper. I had a plan to then write a longer paper with the detailed results, and then life is happening, so that's shelved for now. But of course, again, it's very pertinent. The results depend on which data you put in. One of the reviewers actually, and you can go and find the reviewer comments are publicly available for that paper. One of the reviewers suggested I combine databases, which is what I ended up doing.
Okay. Okay. Thank you.
But in a short, to answer shortly, if one uses a database with very few volcanic products, such as Dubrovino and others, it's very noisy, and statistically the tests will not be passed as much, obviously.
Okay, thanks.
Hi, Nicolas. I have some other questions. So for this this movie you show here is a composition of field. Is that right?
What I'm showing here is the excellent question again. So we've done some work on that, and what we find is that they are thermal plumes, but they do entrain some of the heavy material up as well, depending on the density of the dense material at the base. They do entrain some of the dense material, and I won't digress, but Omer is doing some work on that, and hopefully we might have a paper out soon. Others have shown that. Okay, we're not going into details of that, but others have shown that it's expected that some of the dense material at the base would be entrained by the plume. So it is, and I haven't looked at the details of that for the purpose of this study. Again, here, a couple of flags from me is resolution, number of traces, and so on and so forth, and also viscosity variations come to mind as things to keep in mind when one goes and investigates these problems.
Yes, thanks. And also I noticed the viscosity parameter you select, the viscosity ratio is not very large. So it's, yeah, so if you have a very large viscosity contrast, I'm wondering if the dynamics will be different. Because I know sitcom you cannot explore very large viscosity control, but stack YYR, the code can work for that.
Yeah.
But, so that will affect the coupling and also the moment.
Absolutely, and I'll take that as a comment. It's absolutely valid. It's one of the limitations of that of this study, and so trying to do this again with more modern codes, but obviously, regardless of if one is using Sitcom or any other Sitcom S or any other code, there's a cost, right? What Sitcom S doesn't have is adaptive mesh refinement. So, but tools like RIA, for example, and if they do become mature to do time-dependent modeling, that will be very exciting. But that's where, in my view, there's still a frontier. Already 10 years ago, some of my colleagues Mike was very excited about RIA, and rightly so. And I've been watching that from the sideline, and I've not yet seen time-dependent models, because the reality is that it's an expensive problem to track. But absolutely, this is a limitation.
Okay. Yeah, thank you so much, and good to see you.
Thanks for your interest. Thank you so much. I think you muted, Brian. Or if you're not, no, you weren't muted, but your microphone must not be working.
Can you hear me now?
Yes, we can.
Okay, so I just switched the mics. Thank you. Sorry about that. Yeah, following up on that question, actually to Yanghui's question, you mentioned that the plumes rise fairly quickly, like in about 20 million years or so. So as a non-geodynamicist, that kind of hints to me, I guess, fairly dynamic features. So in a sense, in terms of like initial conditions and let's say running this multiple times, how much do the features, the end features change as let's say multiple runs? I know it's very expensive to run these models, so you probably can't really do a full like stochastic analysis.
Sorry, I interrupted that. No.
Yeah, that was essentially it. Yeah.
No, that's a very good question. So they're both expensive and not that expensive. Okay, so they're affordable enough that I can run a series of models and explore the sensitivity to some parameters. What I found is the main parameters that govern the results are the Rayleigh number as expected, and the point at which I start the reconstruction has a big influence. I have not looked at the details of plumes. I anticipate the plumes, the number of plumes, and I've started work on that actually. The number of plumes depends, as expected, on the Rayleigh number, internal heating. It will also depend on the thickness and density of the basal layer to some extent. The large pattern of the flow is very much driven by the tectonic reconstruction. And what's very important to keep in mind in these models is that the reconstruction has been imposed. The models are not fully self-consistent either. So the finest, to answer more as best as I can, I suppose, the finer structures, yes, they will vary from model to model. And to first order, the results will be more robust. Okay, so from a model to another, the location of the blobs might change slightly, but it won't change a lot. However, if one starts looking at the plume, which is a much finer feature, of course, the location of plumes will be a bit more variable. So yes, that's an excellent point. And perhaps to follow up, I think I would say that perhaps these models are best used to look at first order large scale. I would not argue that in the details they are correct. I think in the concept, what was important to show is that, I think it was actually important to show that it's possible for things to move. Whether things move too fast in these models or too slow is up for discussion.
But you didn't impose the location of the blobs, like in the initial conditions. It was a fairly uniform
correct
initial condition. Okay, that's right.
Yeah, so in these models, that's what I do. Then one could play with that. I don't think the end result will be where was I? I don't think the end result would be that different, because there's a billion years of history. In the earlier models I worked with, I think this was much more of a problem, because these models do depend a lot on the initial condition. What I find though is that the transit time from the top to the bottom is about 250 to 300 million years. So once that's the last cycle, the deep Earth will end up looking quite similar at present day. And so the shift becomes further back in time. I also want to highlight here that there's other techniques that use tomography as an initial condition, and then there's either just a backward advection or on a joint, and there's perhaps lots to do in that space. Each approach will have its limits, but of course, in terms of matching the present day, for example, it would be better. The power of what I've shown here is that it's completely independent from the present day, and then it can be compared to it, and one can assess, okay, well, the match is actually, for these large scale features, the match is actually not too bad, I would argue.
Yes, I agree. That's very convincing. Are there any other questions from the audience? And you can sneak in one in the chat if you would like to.
Hello.
Hello.
I enjoy your talk very much, and your 3D model is really fancy. And it's not my area, and I have no idea where you guys came up with things like that. I'm sure I missed a lot of details. I have a small question. It is about the geochemical implications. And you explained the volcanics near the African bloc by subduction of continents. I'm just wondering, in your model, did you consider the subduction of oceanic crust? Because sometimes the sediment on top of the oceanic crust can give same geochemical signals.
Thank you very much for this question. Thank you. The short answer is no, I haven't yet. And that is something I'm very keen to do. And no, so it wasn't considered in this. A simple reason is that the continents stick around for a long time.
Yeah.
And then just a bit more work, and others have done it before. A bit more work is required to regenerate the continental crust over time. And that's one thing I do plan to do in the future, and I didn't do here. And there's two reasons to do it, actually. One important reason, actually, is to check, well, could the blobs have a lot of oceanic material in them? And I have been a bit blindsided in there, but I think actually, as I mentioned in passing in the talk, some slabs heat up and become part of
for oceanic crust to subduct deep into the lower mantle.
Yep. It's less problematic, it's certainly less problematic than continental crust. So
yeah, exactly.
Yes. So perhaps I shouldn't have put that in the paper. The continental crust, look, it's a possibility here. But then I had two questions today, and it's true that in the details for it to subduct deep down is a problem, because it would have to somehow go through a phase change, and I don't know the details there of composition and whether that's possible.
Yeah.
That continental crust become negatively buoyant at some depth, or it would have to be overcome by slab flux, essentially slab negative buoyancy at all depths, which seems difficult as well.
Okay, thanks very much. Thank you.
Thank you for your question.
And any last questions? If not, I think we're at time. So as a tradition in this seminar, we could ask for everyone who's willing to please turn your camera on. And then Nicolas, if you could stop sharing your screen so you can get a nice tile view of everyone in here. All right, so this is, all right, great. Yeah, thank you very much again for joining us. It's very, very interesting talk. And if you have any questions, any other further questions, I guess you feel free to contact Nicolas, and hopefully we can talk to you and hear from you again soon.
Terrific. Thanks so much for having me. I very much enjoyed the feedback as well. So thank you. It's been a pleasure. Enjoy the rest of your day. And yes, please, as Brian said, if you'd like to, please reach out, drop me a line, and I'll do my best to reply in a timely manner.
That sounds great. Thank you.
Bye, guys.
Bye, everybody.